Okay, this is Lesson 3, Unit 6, second semester, 7th grade math. Vocabulary review. What diagram can you use to find the prime factors of a number? Yes? Not a tree plot. Can somebody help him out? He's very close. Nope. A factor tree. Very good. Here it is. Okay, so I gave you some method. I gave you it's called an algorithm. It's a bunch of steps to make your own factor tree for any number. So for any number, you ask yourself, does the smallest prime number divide into this without a remainder? The smallest prime number we use is 2. We start out with that, and then we work our way up. Okay? And then I'm going to reveal the answers to you for number 2. So right here, we have 15. Is 2 a factor of 15? No. So you go up to the next prime number. The next one after 2 is 3. Does 3 go into 15? It does by a factor of 5. And so our tree branches from 15 into 3 and 5. Now, if all of the bottom numbers of your factor tree are prime numbers, you're done. If it's not, you continue the algorithm. So here, if this 5 was not a prime number, we'd continue, we'd reset, we'd start out with 2 again, and we'd work our way up and continue the tree until we had all bottom prime numbers. Okay? That's a little different than some of those teachers taught, but there's a reason why I taught you that way. I'll go ahead and reveal the rest of the factor trees. Just check it with your work. We did this in the first quarter. Hopefully you guys remember doing this early. I think most students learn this in like the 3rd grade. Okay? When I'm done with this lesson, it's a short lesson. So don't ask me for any passes until I'm finished. What you'll learn: to make and use sample spaces and to use counting principles. Where's your pass at? Could you open that, please? New vocabulary: sample space, counting principle. Why learn this? When you're at a salad bar, you can choose from different vegetables, fruits, and dressings. You may want to know all the possible combinations of ingredients. The collection of all possible outcomes in an experiment is the sample space. You can use sample space to find the probability of an event. Okay, a sample space, I used this terminology yesterday. It's just all the different ways the events can occur. All the possible outcomes, okay?
Excuse me, may I have Talise Arce read for early dismissal, please?
Yes, you may. Okay, so let me give you an example. Here's the example, and then we're going to make our own sample space. So what I need you to do is we're going to make a table to find the sample space for rolling 2 number cubes. One's red, one blue. Okay? We're going to use this to represent all the possible outcomes. And we're going to represent each outcome as an ordered pair. So here's what we have. This represents all the possible outcomes for the red dice. It can land on a 1, 2, 3, 4, 5, or 6. Does that make sense? Okay. So now let me show you all the possible outcomes for the blue dice. Okay. Again, 1, 2, 3, 4, 5, and 6. So if I reveal the first row, you'll see here in this first row, this represents the dice landing on 1 with all the other combinations it could land on with the red dice. Does that make sense? So here, if I roll a 1 with the blue dice, the red dice can also be 1. If I roll a 1 with the blue dice, the red dice can also be 2, 3, 4, 5, and 6, and so on. Does that make sense? So right now we have not all of the sample space, but a part of it. Here are 6 different possible outcomes. Okay? So I'm going to go ahead and reveal the other rows. Similarly for 2, 3, 4, 5, and 6. Now, I want to introduce something that is brought up later in the lesson. I want to bring it up now. It's called the counting principle. And basically, What are all the possible outcomes for the red dice? How many? For just the red dice? There's 6. Very good. And what are all the possible outcomes for the blue dice? 6 again. So the counting principle says if we take the possible outcomes, we multiply them together, what is 6 times 6? 36. So if you look on my table, how many different ways can we roll our dice? Our die. 36 different ways. Okay, now we're going to use the sample space to answer this next question. But before I go on, so far, any questions? Pretty easy stuff. Any questions, though? Okay, so here's the question. I need you to calculate this. And all day long, students, they were close, but I didn't have anybody give me the right answer right away. So I need you to find the probability of rolling at least 1 3, keyword at least 1 3. Now, remember when we calculate probability, it's a fraction, right? So it's the favorable outcomes over possible outcomes. So we already know right now the denominator is going to be what? 36. So can somebody share with the class, what do you think the numerator of that fraction is going to be? And I'll tell you if you're on the right track or not. But so far, everybody all day long has been making the same mistake. They've been close. I haven't had anybody nail it just yet. A day. What do you think?
No, I didn't raise mine.
You don't have any guess, though?
Not yet.
Okay. Olu.
11.
Nice. You're the first class to get it right in the first shot. So far throughout the day, everybody wanted to say 12. How many of you guys thought 12? Anybody here think 12? Most people thought that. Olu, why did you say 11? Did you say 12 at first? Did you think 12 at first?
No, because I knew that I might accidentally double count for 3 3.
That's perfect. Everybody today has double counted something. That's how they got 12. Let me explain what Olu is trying to explain to you. If you look in this column, these are all the combinations where you can get a 3 on the red dice, right? So 1, 2, 3, 4, 5, 6, okay? But now we got to consider all the times we can get 3 with the blue dice. So we already counted 6, 7, 8. We're not going to count this again. Skip it. 9, 10, 11. Do you guys understand how I got 11 now? Does that make sense? So who said no? What's the question?
So you just count down to 3 for red, and then
So I counted, and there's 6 in the column for red. So the dice, for the red dice to land on 3, it happens 6 different ways. Now I'm going to go back here and I'm going to count, well, what about when the blue dice is 3? I have 6 different ways, but I already counted one of them. Does that make sense? So that's why it's 11. Okay? Anybody else have a question? Now, so what would the probability be? It's a fraction. 11/36. Very good. Okay. So here's the next question. Okay. We have a new problem. So we're moving on. All right. Give the sample space for tossing 2 coins. Find the probability of getting heads twice. So flipping the coins, the 2 coins, and having them both land heads up. What's the probability of getting 2 coins landing heads up? First of all, I kind of introduced you early in the lesson, counting principle. Okay, so how many different possible outcomes are there? Dominic?
there are 4.
Nice, there's 4. Let me go back to what I was talking about earlier. So how many different ways can the first coin land? 2. How many different ways can the second coin land?
2.
What's 2 times 2? 4. Now let me show you the sample space. Okay, one of my coins can land heads or tails, right? My other coin can land heads or tail also, right? Does that make sense? So what goes in this box right here? Both land heads up, H and H. What about here? 1 heads, 1 tails. What about here? 1 tail, 1 heads. What about here? Both tails. Okay, so what is the probability of getting Both of them landing heads up. 1/4. Is that difficult? Any questions about this? This has been a pretty easy unit so far. Questions? I thought I might have saw a hand up here. Any questions about this so far? All right. So the answer to that is 1/4. Remember, when you get that fraction for your probability, you have to simplify it. Don't get a wrong answer because you're one step away from getting the right answer. Make sure you simplify the fraction. Yep. Because they said, out of all the possible outcomes, how many ways can it get both the coins land heads up? Well, we see it right here. There's only one situation where I have heads, both of them being heads. Out of 4, so 1/4. Okay? So the bottom denominator is how many different ways there are. The top one is how many times will it happen the way we want. In this case, heads up, both of them. Okay? So look at the next page. Now this is another way to represent a sample space, and this might make more sense, and this is why they had you do that in the factor tree. It's not that we're going to make factor trees, it's just the structure is very similar. So look at this. You can also show a sample space by using a tree diagram. Each branch of the tree represents one choice. Okay, so here's an example. We're going to use a tree diagram. And so river travel. So it sounds like this is like a adventure tour, and they let people choose between 2 types of watercraft, and then they let them choose between some different routes. So let me read the question to you. River travel. Suppose you are going to travel on a river. You have 2 choices of boats, a kayak or a rowboat. You can go upstream on 3 smaller streams. You can go to the north, the northwest, or the northeast. What is the sample space for your journey? Make a tree diagram for the possible outcomes. Now listen, I already explained to you counting principle. So let's figure out how many different combinations we have. First of all, how many different boats can we choose from?
2.
How many different routes can we go?
3.
So how many different combinations do we have?
6.
2 times 3, 6. So here's a tree diagram. Let me show you. It's another way to represent a sample space. And we see for the kayak, if we chose a kayak, we can go north, northwest, or northeast. So here are the possible outcome combinations. Okay? There's 3 for the kayak. And then if I chose a rowboat, there's 3 different combinations for the rowboat. So altogether, there are 6, just like we calculated. 2 times 3, 6. Okay? So we can figure out how many different combinations there are without making a tree diagram if we understand the counting principle. Does that make sense? Okay. So moving along. The question says, suppose you select a trip at random. What is the probability of selecting a kayak going directly north? What's the probability of selecting a kayak going directly north? Adipoju? 1/6. There's 6 different total possible outcomes. There's only one that's a kayak going north, so 1/6. Any questions? Yep. Okay, so it's what are the possible outcomes for one choice? What are the possible outcomes for the other choice? So for the boat, how many possible outcomes are there? How many possible choices do we have? 2. For the direction on the river, how many possible choices do we have there? 3. So 2 times 3, 6. And if you see, we have 6 different combinations here. Okay? And they're all different from each other. Any other questions? All right. Pretty easy. Raise your hand if you have a question. Now, here's the next thing. This is what we just talked about, 1/6. And this, again, is just reiterating what I said about the counting principle. So this is kind of what Jayla was just asking me a moment ago. 6 different possible outcomes. Now, suppose this like adventure tour company said, you know what? We're getting a lot of requests for another type of boat. Let's add that to our choice. And the question's saying, hey, suppose a canoe is added as another choice of boats in the previous example. Draw a tree diagram to show the sample space, then find the probability of selecting a canoe at random for the trip. So first of all, how many different options do we have now? if we add another boat? 9. So what did you do to get 9? You had 3 options for your boat times how many different routes? So 3 times 3 is 9. I'm not going to spend too much time having you guys build this diagram. I will say the first part remains the same. So if you were to add to this diagram, what would the part be? What would the part look like that you're going to add to it? Canoe, northwest, northeast, and north. So it's going to look like this. Okay? And then they want you to find the probability of selecting a canoe at random for the trip. What's the probability of selecting a canoe? Okay, so you said a third, but before you simplified it, what was it? 3/9, and 3/9 simplified to a third. So, very good. All right. And then the book mentions counting principle now. I wanted to introduce it earlier in the lesson just so we're using it throughout the lesson. So, let's move on. Key concept, counting principle. Now the book uses some variables to represent, hey, if you have m options, m choices, and then you have n other choices, you multiply those, that tells you how many different combinations you have in the sample space. Okay? Now, just to kind of align this question with the key concept, how many of you guys been to Subway before? Okay, what's the first thing they asked you? What kind of bread, right? Okay, and then they ask you like, okay, what do you want on the sub, right? So this should make sense to you. Using the counting principle, how many different sandwiches can you order when you choose 1 bread and 1 meat from the menu? So if you look, that's not a coincidence. I circled the first option, I put an M over it. I circled the second option, I put an N over that. Can somebody tell me how many possible combinations of sandwiches do we have? Can I get somebody to raise their hand and volunteer? Please don't call out. Logan, what do you think? How many different combinations? You can move up if you need to. Did you say 30? How'd you do that? Multiplied 5 times 6. How many of you guys got that? Perfect. So we have m times n equals the total possible choices. There are 5 types of bread, 6 types of deli meats. Now, we're going to expand on that question a little bit. So we like options. So the deli counter, the person that manages the deli counter, he said, hey, let's add chicken to the list of deli meats. Now, how many different sandwiches are available? Who can answer that question? Henry?
35.
35. How'd you come up with 35?
Well, there used to be 6 meats, like you add another meat, so that makes 7. 5 times 7 equals 35.
Very good. So instead of 6, we have 7. I worked it out this way. Okay? In this case, 6 plus 1, 7. 5 times 7, 35. Any question? Yep.
So do you have this multiplied it by 5 times 7, then you got 95?
Yeah, I just kind of explained where those came from. Yeah, that's exactly what we did. 5 times 7, 35. So we're at the end of our lesson now. Who can explain what a sample space is? What is a sample space? Who's got it? A day. Are you trying to figure out how to word it? We'll just throw some ideas out, like what's coming to your mind. Maybe I can help you figure this out. It's okay if you're wrong. This is when you want to get wrong. You don't want to get wrong tomorrow during the quiz, but you might have pieces that are there, so we can make it gel for you. So like, what is it? Very, very close. Say it again. You're like, you might have nailed it.
Like doing stuff different ways, like things different ways.
So he's really close. Like almost, I would probably give most of the points for that. Trinity, what is it?
The collection of all possible outcomes.
When you say ways, it's like the outcomes. all the possible outcomes, all the possible ways. So I'm trying to tie in her answer with yours. Okay, so the next one, take a look at this. We're going to complete the tree diagram. I'm going to show it to you. And I'm going to point to different parts of the tree diagram, and I want you guys to tell me what's happening here. It's a tree diagram representing a coin being tossed 3 times. Okay, so over here, in the first toss, it can either be heads or tails. In the second toss, it can go from heads up to heads up again, or what's this going to be? Tails. Okay, what could this be right here? Tails again. So we can have heads up, and then tails, so HHT. And what would this be? Okay, so that means we flip the coin heads up all 3 times. So this would be H over here. Okay, what about this over here? What's going to go over here? H, very good. How about this? What's this going to be? So if we start out, first flip, we got tails up. What's this going to be? H, so the second flip, I have heads up. Okay, so what would this be then? H also, very good. I flip tails the first time, the second time, and then here it's saying the third time I could possibly get a what? H, right? What would this be? Tails, very good. All right, so here is what we got. That's what we just gave the answer and filled in the blanks or the question marks. Now we're going to use this, what do we call this again? Does somebody remember? Tree diagram. We're going to use this tree diagram. It's completed, and we're going to use it to figure out what these probabilities are. So, what's the probability that I'm going to flip all 3 heads? How often do we see that happening in our sample space? 1 time. So what is the probability? 1/8. Okay. What about the probability of flipping tails up all 3 times? We only see it happening once, 1/8. Now this is where you have to be careful, because when we take this quiz tomorrow, they might word it a little funny to throw you off. So look at this next problem right here. At least 1 H. At least 1 H. So let's think about what that means now. If it says at least 1 H, does that mean we have a favorable outcome if we flipped heads twice? 3 times? Okay, so you have to understand what it's saying. So what is the numerator of that? What is the probability going to be then? 7/8, because there's at least 1 H here, 1 H here, here, all but here, so that's 7/8. Do you guys understand? Now, that's very different than the next one. The probability of exactly 2 T's. Only 2 T's. It doesn't say 2 or more. That's very different. So how many favorable outcomes are there? There's 3. Look, this is 3. It said exactly 2, so that doesn't work. This one's got tails flipped twice, so that one works. How about this one? Yes. How about this one? Nope. This one? Yep, I got 3. Nope, nope, nope. So it's 3/8. This is such an easy unit so far. Am I wrong? Any questions about this so far? Here's the answers we just gave. Last question.
If you have one, like let's say you have one boat, one kayak, and then you had a bunch of outcomes on that, could you still do a tree diagram? But like if you only tossed it once, could you still do it all of those ways?
Well, if you just tossed it once, you would just have, for one toss, you really wouldn't need a tree diagram. A tree diagram is if you're trying to keep track of, because you know if you have one toss, it's going to be one or the other, H or T, right? So it wouldn't be necessary to really do a tree diagram just for one toss. It's when you start doing more than one that it becomes a challenge to keep track of. That's what the tree diagram helps you with. Okay, so moving on. Now, the wording of this question, I feel, throws students off. So I'm going to read it to you, but I'm going to try to get you to understand that it's no different than another question. If you toss 4 coins, how many possible outcomes are there? So that's no different than saying, they're saying, hey, toss 4 coins at the same time, but that's not any different than saying, hey, I have 1 coin, I'm going to flip it 4 times. What are the different ways they can land each of those times? How am I going to calculate that? Nathan, I don't think I've heard from you today. What did you get?
I got 8.
8? Anybody else have an idea? Trinity, what do you think? You're saying 4. Now let's think about the counting principle. Use your counting principle for this. You could make a tree diagram, but that's doing too much. And it'll get you there, hopefully, if you do it right, but it's doing a little bit too much. They just want to know how many different possible outcomes are there. So what would I do? I hear some whispers, and they're correct. How'd you come up with that? I flip the coin once. How many possible outcomes are there? 2. I flip it a second time. How many possible outcomes are there? 2. I flip it a third. I flip it a fourth. Now, throughout the day, I've had some students, instead of multiplying it, they added it. The counting principle says you multiply the possibilities. So multiply 2 times 2 times 2 times 2. It's 16. 2 times 2 is 4, and then 4 times 2 is 8, and then 8 times 2 is 16. So, anybody have a question about this? How about this one? So, you have a furniture company. Find the number of different couches that you can make using 16 different fabrics and 8 different patterns. What do you do? 16 times 8. Can somebody tell me what that is? You got it, Anissa? What is it? 128 different combinations. Yep. Because you have 16 different fabrics, but then there's 8 different patterns for these fabrics. So every fabric option has 8 different patterns for that fabric. Does that make sense? So say you have, let me see if I can say. So you have 16 different colors, and then on those different colors you have different prints. Does that make sense? So if I had red, there's 8 different patterns of red I could have. Like I could have a checkerboard on top of that red, and then I got blue, I could have checkerboard, polka dots. Do you understand now? Does that make sense? That's why we're multiplying. Okay? I don't know if I'd want a couch with a checkerboard pattern on it. All right, last but not least. So do you guys know what an architect does?
Yes.
Okay. They design buildings. Okay? So an architect has 3 different widths he can use for a rectangular building design. He also has 4 different lengths to use for the design. How many different designs are possible? Jameson, how many different designs are possible? Turn around, Trinity. It's 12. How'd you get that? Right. That's the end of the lesson. Was I wrong? Easy lesson? Quick lesson.